Hey guys, welcome to a new video in this artificial intelligence tutorial. In this video we're going more in depth with the fuzzy logic controller, and I'm going to show you in the previous video I just gave you a short introduction to what a fuzzy controller is and the different kind of elements inside of that controller. And in this video we're going more in depth with all the different elements in the fuzzy controller. So first here we just we just have a recap here from the last video where we saw an example of a car approaching another car, and then we made a fuzzy set to give the distance to the car in front of us, and then we can control the speed towards that car in front of us. So we have this fuzzy set over here to the right, where we have this extremely close, very close, medium close, little close, or if the distance is okay. So it's the distance to the car in front of us, and then we set up our fuzzy set and our rules. So we divide it into smaller chunks that we can then have a membership function here, which tells us what degree of membership each each set has. So in this case here we can see it's not either Boolean, it's not Boolean logic where we can only have 0 and 1, but here we can have some degree of membership for our fuzzy sets. So in this case here, we can see up here we have 1, but then it gets lower because we get farther away from the car in front of us, but not a 0, and so we don't have this crisp translation from one state to another state, or from one set to another set. So it just gets less and less extremely close, and then it gets more and more very close here, as we can see here. And this is just how our membership function in this case here is defined. And then we have our universe of discourse, which is down here on the x-axis. And in our example from last video, where we had the distance here to the car in front of us. So it's the range of all possible values for an input to a fuzzy system. So in this case here, we have these kind of inputs here where the cars can be in different kind of states for the distance, and then every distance can have some degree of membership in our fuzzy sets. And then from all of this we just set up our rule base, and then we can use our rule base for our controller and use these fuzzification inference and defusification that we just went over in the last video. And these are the topics that we're going over in more in depth in this video, and I'm going to show you how we can fuzzicate our crisp value and then inference with our rule base, and then in the end do defusification to get a fuzzy logic value to a Boolean value and a crisp set again that we can apply to our system. So first of all, I just want to give you an overview over what is fuzziness compared to probability, because a lot of people they think that they're kind of the same, but they're really not. Because if we see the example down here in the bottom, we have 2 bottles, and the question is then which bottle would you like to drink? And A is the set is our fuzzy set here, which is a set of all drinkable liquids. So in the example here to the left, we have a fuzzy bottle, which means that our degree of membership is 0.9, would mean it's not it's 90% drinkable, but the liquid inside of the bottle is 9%, the probability, not the probability, but it should be 90% of the liquid inside of the bottle is drinkable. So let's say it's 90% water and then 10% something else. So it's a pretty drinkable water if the fuzzy bottle has a member degree of 0.9 in case of the fuzzy bottle here. And if we're talking about probability, and we have the bottle here to the right, and we have a probability of 0.9, then we have a 90% chance that this is drinkable, and we still have a 10% chance that it's not drinkable, or if it's acid or something else like that. Where over here it's just 9% of the volume inside of the bottle is drinkable, and then the other 10% could be less drinkable than for example water. So it could be Coke here, and then over here we have we wouldn't drink a bottle of a bottle if we only had 9% chance that it was drinkable, or 10% that it was acid. So like it's very useful to know like difference between like fuzzy models and probability, because they're two different kind of things, and people sometimes they think they're the same, and like think about it in the same way, but they're really not. So when we're talking about like fuzziness, we need to like think about it in the way of like how much degree of membership does this value here contain in our fuzzy set. So why are we using fuzzy controllers, and what can they be used for? So we're often using fuzzy controllers when the process is a non-linear behavior, because then it's hard to like set up a controller like a classical controller, because when we have this fuzzy controller here, we can just set up our rule base, and set up our fuzzy sets, and then have some kind of like membership degree function that we can determine ourselves, and then we can just use our fuzzy controller in that way. And also, if you have no mathematical model, because it can either be like hard to derive, or it changes all the time, and often in practical examples or applications, like it's just really hard to come up with a mathematical model, and sometimes they're like really complex. So like there will be a lot of different kind of like noise to that model that is not like taken care of or taken into account. So a fuzzy controller here can actually like be better than to derive a mathematical model and try to like implement some other controller that needs a mathematical model. And also, if you have like, for example, an expert knowledge, if you want to like implement a controller for someone, and they just come here, like for example in the car example, like if I just talk to like a guy that wants some kind of like autopilot that can like change the speed compared to like how far it is like behind, or another car in front of it. So then the expert could just say to me like, oh, if the car is like far away, then drive at this speed, or like and if it's like close to, then drive at this speed. So like it's easier to set up rules for a fuzzy controller, and then we can just use those rules that is set up by the expert that we want to implement the controller for, and then we just set up our rules and apply our fuzzy controller to that. And also, if you have like a multi-dimensional non-linear relationship, it should be easy to like understand and also like modify the fuzzy controller. So here we have an overview over like the fuzzy controller as in the previous video, where first of all we have a reference input that we give to our fuzzy controller, and then first of all our reference input is a crisp set. And then we need to do fuzzification here, where we convert it from a crisp set to a fuzzy set. And then we have like our inference mechanism here and our rule base that we set up, and then we like infer the value that we get into our controller with our rule base. And then when we have like a value for a fuzzy controller here, we need to like defusificate it, because now we have a fuzzy value. And we need to convert that again to a crisp set that we can apply to our process or in our application, or what we want to do. And then we use our defusification here to get the input to the process here. And then we have the feedback here from the output to our fuzzy controller again. And this is just like how the process and like the fuzzy controller works in an overview. And now we're going to talk about like the mechanisms and also like the elements inside of the fuzzy controller here. So if we just take another example here of a system where we have an inverted pendulum that is balancing on a cart. So the cart here can push like with a force here U, which is the input force here in newtons. And then we can push the cart here, so we're balancing the inverted pendulum here on the top of the cart. And then we have like the stationary position here, which is just like upright here. And then we have like some current angle here in radians, which is called y in this case. And then it's positive if the pole here goes to the right. So then we'll get like a change in the angle. And like the desired angle is again like equal to 0. And initially like it is not in the 0 position, so we've been like initialized somewhere from the stationary position. So if we just like have this assembly system here, and our pole starts to go like more to the right here, we need to like apply some input force here to the cart. So like it will go over here, and it will try to like get this pole together in an upright position again. But then we need to know, like, we need to set up a fuzzy set here for like how big this angle is here and how much input force we need to give the system here. So in case like our pole here goes down here and it's a bigger change in angle, we also need to apply a bigger input force here in newtons to the car, because if it's just like a small amount of force here we give to the car, it'll just like keep going down here, the pole. But if we like push it hard here with a high input force, it will go like to the left here and we'll try to balance up here. But then if we apply too much input force down here, it will actually like just overswing, so the pole here will just go over here, and then we need to like give it a negative force down here, or like push from the other side of the car pole to like if the angle goes over here, and we need to like balance in the other way. So we can set up our rule table for this kind of example here, where we have like the error and then we have the derivative of the errors, which is just the change in error. So like if the error here, like let's say it's a big negative error we have, and the change in error is big as well, so our angle is pretty far away from the stationary point and it's moving kind of fast, then we need to apply a positive input force. And if we just go back here again, we can see that this is the example here where the angle is big and it's changing, like the angle is changing fast, so we need to apply like the biggest force down here to be able to like balance the inverted pendulum here. And then we can just set up the rule table for like all of the different kind of situations that it could be in. So like down here, like we have the stationary position here, and if it's stationary position but the change in error, like if we're getting a bigger change, then we need to like apply a bigger force as well. But if we're in stationary position and there's no change in the error, like, or like it's just still, then we apply no force, because then we're just at stationary position. Or if it goes like the other way, the inverted pendulum, then we apply the negative force down here. So we can set up a rule table here that we can apply inside of us, inside of our fuzzy controller, and then we can use them. We also need to do quantification when we're talking about like a fuzzy controller, where we set up our member degree shift function. And it can actually be arbitrary, like you can choose whatever membership function that you want to. It can be like some kind of trapezoid function, or it can be a Gaussian, a sharp peak if you just want to, like it is only valid for like a short time, like only at pi divided by 4 it is like it is fully true, and then else it just like falls, like it's some kind of like exponentially. We can also have like screw triangle, or we can have like some kind of waves if you want that, and if that like fits onto our fuzzy set that we set up. So often we just use like the triangular function, or like the Gaussian function up here. So in the example we just went over here, we had this error here, and we have like the change in error, and these are the two inputs to our controller. And then we can set up this this membership degree function inside of like our coordinate system here, where we have like our universal diff codes out here on the x-axis and the membership up here on the y-axis. So we can see we divide our fuzzy set into like neck large and neck small. So it's the angles. Here it's the error in the angle. So here like the pendulum is to the left, like it's a little to the left, and here it's stationary, and here it's a lot to the left, and over here to the right, of course. And then we have the radians down here as the error. And then for our 0 here is the stationary position. So if we would be in the stationary position, our membership degree of would be 1 here, with the rule here 0. So we also have the like the same down here, and we just use the triangular membership degree function here in this case. And down here we have the change in error, which is also an input to the system, which is just radians per second. So it's how fast our angle is changing, and it is just like the same as the rule set that we just set up, but we use a triangular membership degree function. Down here in the button here, we can also see like it goes to like minus infinity here and positive infinity here, because if our angle, it just keeps going down, it just goes out to the left, and we're just neck large because we don't have any more fuzzy sets set up. and the same if it goes to the right and just keeps going down to the right. So down here in the last here we have our output from our fuzzy controller, which is like the force here that we need to apply to the card. And then we also like just set it up in our fuzzy set here with neg large, neg small, 0, pos small, and pos large with the triangle of membership degree function here again. And then we just apply those forces when we're in different kind of situation up here as we just set up in our rule base. So this is just like a visualization with the triangular membership degree function of our rule base that we just set up here on the previous slide. So again here we can just set up our fuzzy controller. We have now talked about like fuzzification and our rule base and inference mechanism. But then in the end we need to, when we have made our choice and we have when we get a fuzzy value, we need to defusificate it to get a crisp value that we can actually apply to our process. And first of all, we need this fuzzification here where we map our crisp input values to fuzzy sets, where here we have like it can either be like, here in this case here we have like S of 0, so now our pole is at the 0th position, so we have no value here for the neg large, and we have 0 value here for the neg small, but we have a 1 here for our 0 because we're at the stationary point, so it will be right here, and no values for the rest as well. But let's say here we have like, for example, our S of pi divided by 8, it will be like here in the middle of, like it will be here. So we have like, we're in between like 0 and pos small, so we're in between like two fuzzy sets here. So again we have no values for neg large, neg small, but we have a half here, we have the 0.5, so we have 0.5 for our 0 set here and 0.5 for a pos small set here, so we're just in between these two sets. So this is like how we set up our fuzzification and like determine where we are in our membership degree function. So when we have like our fuzzification, we can then match with our rule base, so which rules in the rule base should be activated and with what certainty. So down here we can, for example, see here if we had like pi divided by 8, we can see like it will be here, and then we have like this 0.5 that we just talked about. But then if we like take the derivative of that error, we can see like how fast the angle is changing. And over here we can see like we have pi divided by 32, and it will be like around here, and it will be like 0.25. So now we have two rules that are activated, but we need to like know like with what certainty we need to activate our rule for. And down here just wrote that this is just a condition that is true now. So if error is 0 and change in error is pos small, then we need to apply the force neg small to our system. So what should we do with the and, because we have two rules that are now activated. So we can either like take the minimum value, so it will be like the most dominant value, and like because like the lowest value will always be like the most dominant value, so we can't say that it is like more 0 than pos small, but because like pos small is more dominant than 0, and we can like be more certain than the lowest value. So this is just like a continuation from this example here, where we have two rules that are activated at the same time. And the first rule here is that the error is 0, as we just saw here, that we are at this point here, and then the change in error is 0.25. Then the force is 0, but we need to like know like what certainty we need to apply to our activation. So we just take the minimum value of these two because we are operating with the and here, so we have two rules that are activated at the same time. So we just take the least value here, which is 0.25, and then we do our alpha cut down here. So our membership degree here in this case for this rule that is activated is the area down here in the triangle that we just cut out with our alpha cut here at 0.25. We can also have like the second rule here that is true, and it is like the error is 0 and the change in error is pos small. So for our neg small here we have like 0.75, and then the force need to be applied is the negative small input force. And then we take the minimal value, which is indeed like 0.75, because we're using this AND operator here, so two rules are activated at the same time. Then we do our alpha cut here again, 0.75, and we get the area down here under. And then when we have these two rules here, we can like put them together. And when we do defusification, we need to convert our fuzzy sets into crisp values. So these grayed areas, or like dotted areas here, like they are the membership degree that is applied in this situation right now. And we wanted to imply the following two fuzzy sets. So as I just said, it's just like the areas down under here in the triangle that is the case now, and it's our fussification that we need to like defusificate to get a crisp values for these values here again. And there are different kind of methods where we can calculate crisp values from one of the examples that or methods that we can use is to use the center of gravity. And there's also like a lot of other methods that you can look up, but in this case we're just using the center of gravity, which is like the point where it's all like in the middle, so it's like the center of gravity, yeah. And then if we just plot it into this formula up here to calculate the center of gravity, we get a value here of minus 6.81, and this value here will be our crisp value for our fussification, or from our fuzz controller. And in this case here, we can see that we need to apply a negative force on our card, like 6.81 Newton to our card to like balance this this pole in this case here for our fuzzy set. So that's it for this video, guys. In this video we have been over like the fuzzy controller and each element in the fuzzy controller, how we can go from a crisp value and do some different kind of stuff in our fuzzy controller with our rule base that we set up, and then get a crisp output again that we can apply to our system. So in this case here, we're just all the time getting an angle and changing angle to our fuzzy controller, and then every time that changes, like we get a new value for our crisp output, which is the Newton that we need to apply to our card. So we're always trying to like balance the inverted pendulum from some given state on top of a card here by applying some force. So this is like how we can like the different kind of steps that is needed inside of a fuzzy controller. And in the next video here, I just want to show you like that we're going to like implement a fuzzy controller ourselves, where we use this as a library or API here that is called fuzzy light in C++. So we can actually like go into C++ and set up our rule base and do different kind of stuff with our fuzzy controller, and also like define our membership degree function and our sets. And then we can actually implement a fuzzy controller, which we can give an input, and then we get a crisp output that we can apply to a system. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification under the video, and also like this video to show the YouTube algorithm that you like this content and you want more of it in the future. I'm currently also doing this algorithm data structure tutorial in C++, or the computer vision tutorial with OpenCV. So if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.